Okay, so really today is just going through problems from practice exams. If you have any specific problems you want to start out with, we can start there. You know, I taped a lot of the problems for practice exam A, so I would think it's probably beneficial to ask ones from B, but if you're having problems with ones on A, feel free to start there. So if I don't have any questions, I'll kind of pick and choose, I guess, and go through a few of these. But if there's any questions that you guys want to start out with, I will take those now. Anybody has any specific ones that they're working through practice exams that they want to go over first? No? No in the chat? Okay.
Can we go over 14 and 15 on practice A?
Yep. So 14 and 15. Let's make sure I've got A here. Yeah, this is A. 14. Oh, okay. Yeah, so you know this specific example is a little different than what we did in class, but it's still if we have kind of this regular generalized discrete random variable. So we've got the number of weeks here. We've got the probability that we see each one of these number of weeks for this variable of how many weeks you get sick in the month of February, right? So you either get sick 0 months, 1 month, 2, 3, or 4. They all have different probabilities of occurring. So the very first question is, what's the expected number of weeks an individual gets sick in February, i.e. the mean number of weeks sick? Right? So we have just this regular discrete random variable. We want to find the mean. One thing that you might originally think is, okay, I'll take these number of weeks, I'm looking for a mean, I'll just add all the numbers up and divide by the number of numbers, right? So I might go 0 plus 1 plus 2 plus 3 plus 4, divide that by 5. So the reason why that's not going to give you the correct answer is because we're dealing with something that's going to happen in the future. Each one of these outcomes has a different likelihood of occurring. Do you have a question? No, okay. So we can't just simply add them up. We need to weight them by however likely they are, however likely it is that they're going to occur. So let me see if I can, this one I might just pop up here and try to make this big for the video. Everyone can kind of see in person what we're doing here. So we've got all these different outcomes. All we're going to do, so we'll go to, we need a reminder, we'll go to that formula sheet. Go down here, here's our generalized kind of discrete random variable equation. Here's our mean, here's our variance. So all we're going to do is go through every single outcome, multiply by the probability the outcome occurs, and add them all up. Right? So what that means is we're looking here, is we're just going to take the very first outcome of 0. Right? So let me write this bigger. Let me write this a little bit bigger since I got plenty of room. So we go 0 times, what's the probability 0 occurs? 0.45. Add in the next outcome of 1 times, what's the probability that 1 occurs? 0.25 plus 2 times the probability 2 occurs, which is what? 0.15 plus 3 times the probability 3 occurs, 0.1. The last outcome, which is 4, times the probability 4 occurs, which is 0.05. Okay? So if we do that, we get what? 0.25 plus 0.55 plus 0.3, 0.85 plus 0.2, so 1.05. I'm doing the math in my head there correctly. I guess we could pull up the answer just to double check my mental math here. Yeah, 1.05 if we end up entering that into our calculator. Okay. So all we're doing there is going through each outcome, multiplying by the probability it occurs, and then adding them all up. You can do this in intermediate steps. Like I wrote this all out like in one line. I could find this, write it down. Right? So this is 0, this is 0.25, this is 0.3. I kind of go through intermediate steps, write them down, and then add them all up. Or I could just do this all kind of at once. Okay? Any questions on that one? Okay with that? All right, so this next one. So this is one where if you had gotten 14 wrong, you're for sure going to get 15 wrong. Because if I'm trying to find a variance with the wrong mean, I'm going to be finding the wrong deviation from the mean, right? So this one asks for well, not the variance, but standard deviation, same idea, because the standard deviation is just the square root of the variance. So if I want the standard deviation here, what I'm going to tell you is I'm going to give you an assumed true mean. I'm going to say, I don't care what you found in 14. Assume that you found the answer was 2, right? Assume that the mean is 2, okay? Now, when I give you these assumed true values, and there's not as many of them here in the first exam. In the second exam, I'll probably give you a lot more just to kind of we're all starting off on the same page. Don't read into them at all. Like here, I gave you the assumed true value of 2. The answer was not 2, right? So don't like look at this and go, oh, well, it's probably 2, so I should be answering. No. I'm just giving you a value here, and it has nothing to do with what the correct answer actually is. It's probably actually to give you a value that's a little bit easier to deal with, right? 2 instead of 1.05. So if we look at this, first of all, if I'm looking for a standard deviation, which of these can I rule out right away? B, right? Why? Because if I'm looking for a variance or a standard deviation, it has to be positive. The lowest it could be is 0, right? So right away, I've got this down to, even if I just want to guess, now I've got guess now to 3 instead of 4, right? So from there, what can I do? So I go to my formula sheet. Here's the variance for discrete random variable. It's going to be very similar to the regular variance. So I still look at the outcome, subtract the mean, look at that deviation from the mean, square it. But then I multiply it by the probability that I saw that X outcome occur, right? Once I do that for every observation, I add them all up. Here it's actually a little bit easier, and I don't have to divide by anything because I should be dividing by the sum of my weights. But my weights are probabilities. Those probabilities should always add up to, if we add these up, they should add up to 1. So I'll go through each line. 0. So the very first outcome of 0 minus that assumed true mean of 2. I then multiply that by the probability that I saw that outcome of 0. I'll then add to that the next outcome, which is 1. Minus that mean of 2, square it. What's the probability that 1 occurred? 0.25. And then I just keep going through each single one of these outcomes and keep repeating this process, right? And then just add them all up. Okay. So 0 minus 2 squared times 0.45 plus 1 minus 2 squared times 0.25 plus 2 minus 2 squared times 0.15 plus 3 minus 2 squared plus, or times 0.1 plus 4 minus 2 squared times 0.05. Okay? So that's kind of the process that I'll use. I didn't write it all out, but I kind of gave you the beginnings and the how to start attacking this. If I do that, let's see. I'm going to double check so I can work along this with you to see if we can find any pitfalls that I might run into as well. So that plus 0.25 plus 0.1 plus so I believe the variance is 2.53. So I'm got to read these carefully. If I were to answer 2.35, sorry, 2.35, not 53, I won't get this correct, right? Because I'm not looking for the variance, I'm looking for the standard deviation. So then the last step I would have to do is, once I have 2.35, just take the square root of it, right? If I take the square root of it, I should get 1.53. Okay. Any questions? I know I didn't work it out completely, so if there's any kind of questions, make sure you ask. So let me make sure I can see the chat too, since someone. Okay. Any other questions on those two? So these should look very similar to a weighted mean and a weighted variance example, which I believe is what we have all the way up here on problem 4. We have a weighted mean example. It's just up here, our weights weren't probabilities, so we still had to divide by the sum of our weights. Once we're dealing with probabilities in this discrete random variable, now we really don't have a denominator because the sum of our weights or probabilities should always be 1, right? Which meant we could use these formulas, and I think made life a little bit easier. Okay? So any questions on that one before I keep going? Since we're already doing these, I'll do this last one as well. This one should be pretty easy. I would hope on an exam, this is near 100%. Most of you all get this correct. The only issue is paying attention to the wording and also equality. So what's the probability, I guess I said you here, but what you can think of as that someone is sick for less than 2 weeks in February? Well, the probability that X is less than 2 is what that's saying, right? Less than 2 weeks, not including less than. So what are the only outcomes that fit this criteria that we could see? Go back up here. The only outcomes we could see that fit the criteria of being less than 2 would be 1 or 0. The probability we see 1 is 0.25, plus the probability we see 0, right? This or this. And this is kind of in the background. What's floating around, this is kind of a review of probability stuff. So if I have the probability of A or B, we said we could rewrite that as the probability of A plus the probability of B minus the intersection, or A and B. But here, when we're dealing with these discrete random variables, we can only see one of these outcomes. So I can either be sick exactly 1 week, or exactly 2 weeks, right? It's either one of those two. And so really here, when we deal with this discrete random variable, because we only observe one outcome when it actually finally happens, our intersections are always 0, which is why we said when the event is something like, is X less than 2, well, this should have been X is less than 2. What I'm really saying here, am I sick for 0 weeks or am I sick for 1 week, right? Those are the two things that would fit that criteria. And so that's why I'm simply just adding up those probabilities. So I take the probability that it's 1, add that to the probability that it's 0, and I get what, 0.7 here? Now, I have to be careful with these equalities because if I looked at this and said, you know, what's the probability I'm sick for less than or equal to 2 weeks, and I would have included 2, well, then I would have had, what, 0.7 and then plus 0.15, so 0.85. I'd be a little bit off there. So just be careful with your equalities there, and if you're careful with the equalities, I think, you know, these should be a pretty easy question. Right? And I could go the other direction too. I could have said, like, what's the probability someone is sick more than 2 weeks, in which case you would just say, okay, what fits that criteria? Well, either 3 or 4, I would add those probabilities up, and it would have been 0.15. Any questions on that one, or if I could change something or ask something slightly different? Okay? Yeah, and you'll see one like this, you know, kind of a set of questions like this, and like I said, hopefully this is an easy one. Add some easy points for a lot of people. Any other questions you guys want to start out with? You can type in the chat, speak up. I can hear you on Zoom. Okay. I think we've worked through, at least either in class or kind of those videos, most of these. One that we didn't do that I'll cover is this one right here, 13. I don't believe I have this one up there. So I'm going to go through this problem 13 on practice exam A. I guess we kind of already have the answer here, so I could switch back so we can't see it. But so I'm given this kind of diagram, and I'm asked for, I got cut off here because I was typing some stuff. So let's get this all in one line. All right. So I'm asked for what's the probability that event B occurs here. Okay. So this entire experimental outcome space, this entire rectangle, I know has a value of 1. Right? Because it's every single possible experimental outcome, it represents probability. So if I add up all those probabilities, they'd add up to 1. So I know this rectangle, the area is 1. I'm told that this light blue area is the intersection of the complements. You don't have to worry about remembering this. You'll be kind of always given that that's what that is, right? So I'm told this light blue area is 0.1, which means that I know the area in the circles has to be what? Yeah, if this entire experimental space is 1, and the area outside the circles is 0.1, the area in the circles has to be all right, so, I mean, this isn't like a trick question. Let's break this down. Let's make it easier, okay? If this is an area of 1, and I tell you this is 0.25, what does the rest of this have to be? 0.75, right? Because it fills up the entire, it's the same idea that we were doing here, right? if that light blue area is 0.1, the area in the circles has to be 0.9, right? Because it fills out the rest of that entire experimental outcome space. So I can do this a couple ways. Okay? I'll show you kind of the shorthand way first. I think if I think about it that way, where I know the area in the circles is 0.9, I think it actually makes it a little easier. So what is the area in these circles? What's another way I could think about that in terms of probabilities? That's the probability that I'm either in A or I'm in B, right? I'm in either one of those circles, okay? So because we know that area is 0.9, and I know that that's representing the area of being in either A or in B, I also know what's another way I could write the intersection, the union of these two events. Well, if I go back to my formula sheet, the union of two events is the sum of the two events minus what we double counted or minus that intersection. Okay? So I'm just going to write this out. This is the probability of A plus the probability of B minus the intersection of those two things. Okay? Well, I was given two of these in the problem. Right? So if I go back, which two was I get? Well, I had the probability of A is 0.4, the probability of the intersections is 0.2. Right? So I'm just going to plug those in. So this is 0.4. I don't know what the probability of B is. That's what I'm eventually looking for. And the probability of intersections is 0.2. At this point, it's just a little bit of algebra, right? So I've got what? 0.4 minus 0.2, so 0.2 on this side, so I'll subtract that. Once I subtract 0.2 from this side, all I'm left with is, I kind of ran out of room here, but I have the probability of B being equal to 0.7, right? Once I do a little bit of that algebra and solve for what I don't know. There's a little bit of glare here, so it's not really helping. This is the probability of B is equal to 0.7. Right? Any questions on that one? Now, another way I could have done this is kind of start out making it a little bit more complicated. Instead of thinking about the area in the circles was 0.9 originally, I could have started out with, I know that entire experimental outcome space of 1 was composed of what was in either one of those circles plus that light blue area, which I knew was the intersection of the complements. So I'll switch the screen here in a second for those of you on Zoom. Right. So I could have just plugged that in, right? I know that the area in the circles plus the area outside the circles is equal to 1. Then I could have plugged this in. I just would have had a couple more moving parts because I know I was told that was 0.1. But if it was easier to kind of look at that and say, okay, I know that the area outside the circles, I'm given that value. I know that's 0.1. So I know that that plus the area in the circles has to add up to 1. So what has to be in the circles? 0.9. And then I can kind of start out kind of eliminating one of the kind of, additional things I would have had to keep track of, right? But either way, you'd arrive at the same answer. It's just if I started with this, I'd have kind of one more component in there that I have to plug a value in for. But either way is fine. Okay? Any questions on that one? More as we move on, kind of wanted to start at any other given question. On practice exam A, 17, let's see what 17 is. Okay, so actually let's do, since I had worked through this one, let's do the exact same one, but let's do practice exam B. This is not what practice exam B is supposed to look like, is it? Hold on. I think I have that for the other section. So let me go to files and make sure we're dealing with the right practice exam here. Oh no, that is practice exam B. Okay. So we'll go down here. 17, yeah. So we have here that 40% of credit card consumers carry a balance from month to month. Suppose we interview 10 credit card customers. What would the expected number of customers be? So here, for those of you in class, let me make this a little bigger so it's easier to read for everybody. So here we're dealing with something where we either see someone carry a balance or they don't. So that's kind of our success failure. We know that we're looking at 10 individuals, and the probability that any one individual that we select at random has credit card debt or carries balances month to month is 40%, or an underlying probability for any one person of 0.4. So this is a really good example we can use that binomial distribution for. So we go to that formula sheet. Here's our binomial distribution functions, right down here. Now, we're just looking for the mean, or the expected value, so that's as easy, or that's as simple as just taking the number of trials, multiplying it by the product success. This was the idea of if I flip a coin 100 times, I know the expected, or the most common number of heads I would see would be 50. And I intuitively did that in my head because 100 times 0.5. But here, we're going to have not as nice or not as easy kind of number of trials or probably success, potentially. What's my number of trials here? I'm looking at 10 people, 10 customers, so my N is 10. My product success for any one person would be 0.4. So 0.4 times 10 just gives me that expected value of 4. All right? Or if I'm thinking about how do I find that mean of a binomial, just N times P. My N was 10, my product success was 0.4, and so that gave me the mean of 4. Right? So once you've identified that you have kind of this binomial example where you're looking for something occurring, right, and the number of times out of 10 people you see that occur, right, the number of times out of 10 people you see someone have kind of carrying a balance month to month, then we know we can use these binomial equations. Right? Now, going into the exam, I would save a copy of this formula sheet as opposed to like working from Canvas or something like that. Because actually, I think if you pull the one up on Canvas and you just try to observe the Word one, it looks real terrible. It's because I don't know, the web browser doesn't like my Word document. I don't know if it's the edition or what, but if you download this, it looks okay, right? And if you really wanted to, I don't know, you could like print this out and start writing like next to these, here's my binomial, or even if you wanted to like kind of type it in or insert, you know, some words to make it easier, like these are my binomial, these are my, oops, discrete random variable. I don't know how you want, you can type these in or you can, write them next to it, insert like kind of a word thing so that it doesn't kind of change where everything's at. Going into the exam, that might make it a little bit easier. But once we know we have these as our binomial equations, the variance would be really easy to find as well. So if we look at the next question, I believe the next question there, practice exam B, was what's the variance? Well, still dealing with a binomial, so we look at that formula sheet, it's just N times P times 1 minus P. So 10 times 0.4 times 1 minus 0.4. I believe if we do that, we get 2.4, but that's off the top of my head, and I could be doing the math wrong in my head. No, you do get 2.4, there's the variance, okay? And the only other kind of, I guess, quote unquote, trick I could do there, or thing I could change for the exam, is instead of asking you for the variance, maybe I ask you for the standard deviation, in which case, all you would have to do is take 2.4 and do one more step, which is take the square root, right? Okay. Any other question? And that was from practice exam B, but hopefully it's similar to the one in practice exam A, and that kind of answers your question there. Any other ones we want to, specific questions you want to start with? Yeah. 11 and 12. Yeah, we could do, I think we left off last class, but we didn't get to completely go through all of them. So I will I'll do the one from practice exam B just to give us another idea. And I'll actually probably just work through 11, 12, and 13. So I give you kind of a couple different looks at that base theorem too. So, wait, is this A? No, this is B. Good. So we're going to work off practice exam B now, and we're going to work through 11, 12, and 13. So, blah, blah, blah. We're worried about steroids. A manufacturer claims that the probability that a drug test shows positive, given the athlete is using steroids, is 0.95. Okay? So this is one of those ones where we're given some information and then ask some questions. So I'm going to just write out what we're given first. Okay? So the first thing we're told is what? Given that someone is using steroids, the probability the test comes back positive, right? So given that the athlete is using steroids, the probability the test shows positive is 0.95. So here I'm going to write out the probability that given someone is using, the probability the test comes back positive, right, is 0.95. Okay. So given, this should be a straight line, given that someone is using, the probability the test comes back positive is 0.95. Okay. The next thing we're told is, however, the probability the drug test shows a positive result given that an athlete is not using is 0.01. So now we're dealing with, given that someone is not using, the probability that we see a positive test result was what, 0.01? Okay. And you know, if there's a glare on, for those of you on Zoom, if you can't kind of make out any of this, please make sure you ask. Hopefully, as I'm saying it and writing it, that makes it a little bit easier as well. The final thing we're told is a recent article suggests that the probability a random person is using steroids, we select someone at random, the probability that they're using steroids is 0.15. Okay. Now, one other probability we could very easily get is if we know the probability someone is using is 0.15, what's the probability that if we choose someone at random, they're not using? I'm either using or I'm not. So if the probability I'm using is 0.15, the probability I'm not using is, whatever gets me up to 1, or 0.85. So right away, this is just kind of the easy information we're getting. We could derive some other information from these two, and I'll actually type this out and kind of show you, if I was doing this, how maybe I would maybe set this up, not just the probability tree, but we could do it a different way. But I think for the first one or two, we just need this information. All right? So here's the information we have. Now let's start working through the actual problem. So number 11, I would always start out writing, what am I looking for? Okay? So what I'm looking for in 11 is what's the probability an athlete is using steroids and the test comes back positive. Right? Now, I wrote the word "and" in there. I could have also thought about this as actually write my intersection sign in. So if I go to equation here, there's my "and" sign. I could have written it like this. Either way means the same thing. If I write it this way, maybe it reminds me what equation I can use for my formula sheet. So I go to my formula sheet, and I say, okay, I'm looking for the intersection of two events. So the intersection, these are special conditions. Here we go. The intersection is the conditional probability times whatever I'm conditioning on. So my event A is that the person's using. My event B is the person tests positive. Okay. So I'm going to move this over here for a second. We're going to keep this up there just so you can kind of see this all at the same time. So my event A is using, my event B is that they test positive. So I'm just going to write this out in the context of my example, right? So I would want the probability of B given A, so the probability the test comes back positive given that the person is using, and then multiply that by the probability of A, or the probability of what I'm conditioning on, which is the probability that this person is using. Right? So all I've done there is write out what the problem wants. Once I know what I'm looking for, if it's an intersection, it's usually a little bit easier. I can use this equation here. use my events A and B, whatever those happen to be, and write this out, this multiplication rule out in the context of my example. From here, if I go back, okay, what was the probability someone was using? That was just right here, 0.15. And then the other thing I wanted was, given that someone's using, what's the probability the test comes back positive? Well, given that someone's using, the probability the test came back positive was 0.95. So I just plug those in, 0.95 times 0.5 there. And I'm guessing that is, wait, no, not 0.5. Someone should have corrected me. It's 0.15, right? So if I do that, I think that's probably 0.09, but I'm not 100% sure. So let me double check here with my calculator. So that's actually about 0.143. I think it's actually 0.1425, but if we round to that third decimal, kind of however the answers are displayed, rounding it to that decimal, I should get, oops, 0.1425, which if we round it, we can say is 0.143. Right? Any questions on that one or anything that I did there? I follow along with, first we just write down what we have. And the next step is in the question, write out what probability that you're looking for. And then usually you're going to have to probably use the multiplication rule if you're looking for the intersection of two events there. Okay? So we'll do one more, really similar to that, which is 12. So 12 says, what's the probability an athlete is not using steroids and test positive? So this one should look really similar. So what's the probability that someone is not using and the test comes back positive, right? And I could switch this and sign once again to my intersection, but if I wanted to. I'm just writing this out and I can remember that, that's fine. If I'm writing this out by hand or something, instead of the word and, I know that just represents this symbol for the intersection of those two things. So now here, oops, I'll write this out. I have another intersection, so I go to that formula sheet. Once again, same equation. So now I have my A, my B. I'm going to rewrite this as a conditional probability of those two times what I've been conditioning on. So the probability of B, right, would be that the test comes back positive because B is what comes second there. Given whatever A is, which in this example is not using, times the probability of what I'm conditioning on, or the probability of A, so that's not using. And now that I have this, I say, well, okay, once again, what's the probability someone's not using? I wasn't directly given this, but remember we said it's pretty easy to derive that. So I can plug in 0.85 here for this probability. And then given that someone's not using, the probability the test comes back positive, I was given that as well. So this is one where actually I didn't have to do any of the probability tree stuff. Everything I had was right there. So what? Equals 0.01 times 0.85, right? Or guessing that's about what? 0.009 if I round that, 0.01 times 0.85. Yeah, so this is right, 0.0085, which for rounding the second decimal, oops, would be 0.09. So let me get rid of some of this so we can see all this on one line. Oh no, I gotta delete more stuff. Where's some spaces I can get rid of? No, all right, one more space I can get rid of right here. There we go, okay. All right. So it rounds that third decimal, okay? Any questions over any one of those two? They're very, I mean, these were very, very similar examples, just slightly different, right? One was using, one was not using. Does that answer the question? Take that as a, yeah. So let's keep going. We'll do 13, probably a pretty good indicator when I'm dealing with a problem, like an example like this. Format's pretty similar in all these practice exams, so you can kind of notice once we get to this one here, it's probably going to be we have to use Bayes' theorem, right? So I'm now told, given that the test comes back positive, what's the probability the athlete is actually not using steroids? Okay. Well, just going to write out what I'm looking for. So so that's the first thing, right? Given that the test comes back positive, what's the probability the athlete's not using? So I go not using, right? Got my state of nature, my outcome of this test. If I go to my formula sheet, right, I'm looking for these conditional probabilities, specifically in these examples where I'm also given other conditional probabilities, right? That's what we started off with here up on the board originally. I'm probably going to have to use this Bayes theorem. So the way in which I would approach this is once I have this conditional probability, I know I need to use Bayes' equation here, identify what my S is and what my E is, and then just write this out in the context of my example. Okay? So I'm going to leave this over here on the side, and I'm going to type it out. Just so I think it's a little bit easier. I've got the information here I can refer to later. I'm just going to type this out just like I would write this out on paper. Okay? So here's what I'm looking for. And actually, I'm going to do one more thing just to make it a little bit easier. Here's my S, and here's my E, right? So when I'm looking for the probability of S given E, I've now just got it written out in the context of my example. So the first thing I'm going to do is I'm going to write out what's in this numerator here. Okay? So the probability of S, my S is that the person is not using, right? Times the probability of E given S, so my E is that the test comes back positive, given my S is that they're not using. Okay? That's my numerator. Let me see if I can do this. So then, what's going to be in my denominator, right? We notice it's the exact same thing at first, right? It's the exact same thing as my numerator, this first component of the denominator. So I would basically just write this all out again, right? So I'm going to copy and paste and cheat in Word, right? I'm just going to write all that. It's the exact same thing in my numerator. The second part of my denominator is what's the probability of S complement? Well, if S is not using, what would S complement be? That the person is using times the probability of E given S complement. So E is still that test comes back positive, but now it's given S complement, which my S complement, if S is not using, would just be that the person is using. Now, I don't have this here, so I can try to, actually what I'll do, this might help. Let's go to insert an equation here, just so it makes it a little bit easier for you guys to see. I'm going to put the numerator up here. I'm going to put the denominator that we just typed out right here. Oh, why is it not like that? Control. There we go. All right, so this is what I'm looking for, right? It's just Bayes' equation written out in the context of my example. Okay? So I put this up here and show you the screen here in a second. Hopefully we'll see that once I go to what I was originally given, first thing I need is the probability someone's not using. That number's right here, plug in 0.85. Given that someone's not using, probably the test comes back positive. That's right here, that's 0.01. This is the exact same thing, so 0.85, 0.01. What's the probability someone's using? 0.15. Given that someone's using, what's the probability the test comes back positive? That's 0.95. And really what that represented was, the numerator here was the people who get a positive test and we're not using the drug. Because remember, this is the exact same thing that we actually found right here. This is the probability that someone tests positive and is not using. Divide that by the number of people who are not using and test positive, plus the number of people who are using and test positive, because that was what we found in 11. People who are using and test positive. It's the exact same thing. So those first two questions are kind of looking at these intersections, because eventually once you get to Bayes' equation, what it's really doing is saying, look, you're going to get a bunch of positive test results. Some of them will come from people who were using, correct positives, and then some will come from people who weren't using, false positives. So we want to know the composition of that group, because when I look at a positive test result, I don't want to damn someone for like using steroids if in fact the bulk of people with a positive test result actually weren't using, right? And so I can kind of get an idea about that from, we'll divide the, these are probabilities, but we can always think about, we've taken contingency tables, turned frequencies into probabilities, we could kind of go the other way as well. So it's almost like you're taking the number of people who test positive and were using and divide that by the total number of people who just got a positive test result, right? Those who tested positive and were using, and those who tested positive and were not using, okay? So once we plug those values in there, I guess I could write out here, I'll type out, all right, once we plug everything in, we would have what? 0.01 times 0.85, divide that by 0.01 times 0.85, plus probably someone was using was 0.15 times 0.95. Right? So once we do that, I don't know the exacts, but let's look it up. So 0.01 times 0.85 divided by 0.01 times 0.85 plus I can't remember all these off the top of my head. I think it should be 0.056 once we enter that into our calculator. Okay. Any questions on that one? How I set that up or any, I don't know. Anything different I could do there? Like I said, I'm typing this out here, but you could write this out. It's the same thing you do if you're writing this out by hand. And it's a little bit easier. I've got all the information up here on the board that's being displayed. If you're kind of watching this video or you're here in class, we have it up here and I'm working through it. If you're working through it by hand, write all that stuff at the top, right? So you have all the information to work through those next 3 problems. And you just continuously refer to those and plug your values in. Okay. Any other questions? Hopefully that helped with 11 and 12 on practice exam A as well. I think we did 11, but we didn't get to do 12 on Friday, but it's the exact same sort of setup. Right? Now I could have made this one a little bit tougher, right? What if I had asked instead, what's the probability that the test comes back negative? Well, now the problem is when I write this out in the context of my example, I don't have any probabilities that the test comes back negative here, right? But if I know, I'll erase this for a second since we have this. Let's just take that very first thing I was given. Right? The probability that, given that someone was using, the probability the test came back positive. So if I had instead wanted to look for whether or not the test was negative, I would have had all my E's here be, is the test negative? I didn't have that information. So here, if I condition on the same thing, so given that someone is using, right, the person in front of me, they're using steroids. The probability that if they take 100 tests, 95 of them will come back positive. That same person who was using then, what's the probability that they would get a negative test result, or think about out of 100, how many would come back negative? Well, if 95 of them would come back positive, we're not dealing with any inconclusives when we're dealing with these examples, and 5 of them would come back negative, where the probability has to be whatever would kind of get me to 100%. Right? I use that idea of taking 100 tests just because it kind of puts it some numbers, some actual frequencies to it. Where if I condition on the same state of nature, which is essentially saying I'm looking at a person doing the same thing, right? They're still using steroids. If I know the probability that person gets a positive test result, I know the probability they get a negative test result would just be 1 minus that. And the same idea for the people who are not using. If I continue to condition on the not using, I would have just taken the 0.01 and subtract that from, so 0.99 would be the probability they get a negative test result. And now I could answer questions like this, right, that have a negative test result in them. Okay? And this was one of the things we said, if we construct this as a probability tree, we could get those two if that helped kind of organize it and remind you, oh yeah, we're conditioning the same thing over on this side. You could do it that way as well. Any other questions on this one?